Hello, and thank you for joining our webinar on reverse osmosis systems. My name is Abby Rogers, and I will be facilitating this webinar. If you have any questions during the presentation, please submit them using the Questions tab in the control bar, and we will respond to them at the end of the presentation. I will now hand this off to Ryan Reimer, Product Manager for Dry Steam.
Good morning to some and good afternoon to others on East Coast or elsewhere. Thanks for joining us today. This is the third part out of three. Particularly my favorite technology to talk about, since there's so much to talk about with reverse osmosis. So some of it will be review on water quality if you attended our previous two, either on softening or dechlorination. Again, my name is Ryan, and I'm the product manager for water treatment and adiabatic technologies at Dry Steam. So some things that we're going to cover today, we're going to talk about water quality in general. As we look at different goals, we need to understand where we're starting from and to really understand about where we need to go with water. The purpose of water treatment, I'm sure if people didn't need water treatment and spend the money on it, they wouldn't do so to save costs, but a lot of our goals in different applications require us to do something to the water to make it more acceptable for the application. Go over reverse osmosis description. By no means are we going to go super in depth on this one from a design perspective. This is high level overview to understand where it's used, how it's used, and some top level descriptors in reverse osmosis. There's plenty of content out there. The technology's been around and commercialized at least since the 70s. So plenty to talk about. Then applications. Where are we using this? Where is this a good offering? How can Dry Steam play in that with our reverse osmosis offering? Followed up by the maintenance expectations regarding this. If you've never dealt with an RO before, it's not plug it in and forget it for the rest of your life. There is some tending to make sure it's operating properly, just like most pieces of equipment. So the biggest thing about what the impact is on water quality is we have goals and our end users have goals to maintain equipment, whether that's a humidifier, whether that's heat exchangers or lab equipment, etc. One of the biggest things is the maintenance impact. The water quality has a huge part on this. In these pictures here, we're talking about calcium carbonate, which is the most typical thing for a scaling potential as we're boiling water. And really that decreases your effectiveness in a lot of applications regarding scale. And obviously when you want to gain that efficiency back, you have to perform maintenance on that, whether that's a chemical cleaning or some good old elbow grease and getting in there and scraping off that scale from different surfaces. So some factors affecting scale formation. I talked about this one specifically in the softening presentation. I'm going to give my analogy again because it's very applicable to both technologies. So temporary hardness is the piece that falls out of solution, right, in the water, and its relationship to temperature is inversely soluble. So the best example that I think of is the difference between like sugar in your tea is more soluble as you heat it up. It's easy to dissolve. Where calcium carbonate's the opposite. As you heat it up with heat exchange processes or other process equipment, it's inversely soluble. So it wants to fall out of solution. Some temperature increases, as the temperature increases, it provides that energy to react. Scale is formed and then precipitate out typically on the hottest part of the system. This next slide talking about water quality. As most people do nowadays, it seems like if I ask, well, what's in your water? What challenges do we have? What challenges do we pose? The first thing people tend to do nowadays is Google. So I Googled Eden Prairie's water quality from our city where we're located. And this is what came back. And the thing that I really want to describe here is these things typically don't have any weight in, good process equipment or for heat exchange equipment or for use in a lab or use for growing plants, for example. This is really focused on the consumer in mind. Is this water safe to drink as a human, right? As we're drinking this water. So the top things, disinfection byproducts along with fluoride that they're adding to the water. Middle table is chlorine. We talked about that in the dechlorinator section of this three-part series. The important thing to note here is, yes, it's present. Yes, we need to take it out before reverse osmosis. That chlorine can oxidize the surface and essentially take away its effectiveness. So we definitely want to make sure that we're cognizant that we need to treat this before going into RO. The bottom two are heavy metals relating to your overall health. The things that we don't see on here and that I like to mention, so when we talk about scale, we talked about calcium carbonate, so that has two different components. One is calcium from a water quality perspective. The other one is alkalinity, which is part of that carbonate family. But there's other things like chlorides, if any of the equipment has stainless, componentry, the overall pH of it for general corrosion's sake, the total dissolved solids. All these things are very important, especially when the end user needs to get to the reverse osmosis type quality. And I'm going to go over some terminology here in next slide, actually 2 slides. And we'll talk about what permeate means, what that term means. So why is water treatment necessary? So we touched on this in the very beginning. The top left picture is scale forming in this pipe. If we decrease that pipe diameter with all that scale, do we really think that our system is going to be performing to its utmost maximum capacity? Probably not. We're going to get increased velocities there and obviously scale things that we don't want to. The top right photo is a depiction of iron or corrosion. We obviously want to minimize corrosion. We want to maximize our equipment life. A lot of these things that are going to use RO water need to last a long time. They're not inexpensive pieces of equipment. So we definitely want to make sure we minimize corrosion. The bottom left is in particular to chloride corrosion on a weld. So unlike softening and dechlorination, the actual chloride ion is only removed with a few technologies, one of which is reverse osmosis. And lastly, the other thing to consider when we're talking about overall water treatment is the effect that bacteria and viruses can have on that, and is it safe to be around, obviously, people. The chlorine is one thing that's added to city water that helps negate that, but we also need to keep in mind that once we take out the chlorine, what are we doing with that water? Are we leaving it stagnant? Is it in sunlight? All these different things. So recommended supply conditions, this is different for each piece of equipment. It's different for humidifiers versus steam boilers, whether that's a fire tube or a water tube, different than cooling towers, different than a lab's need. But really here, we're looking at what do we need to get to satisfy that inlet condition. This is an example of a humidifier required water type, depending on this. And this is something where dry steam can help, the reps that are on the call and end users understanding, well, what do I need to know to make sure that this RO is gonna have a good rejection, etc. So we can supply a testing checklist of what we recommend, along with other people in the industry that do this. This is quite common. Another just quick depiction, I'm not gonna sit on this slide too long, but essentially the biggest takeaway as we talk about reverse osmosis is it provides nearly clean water. And what I mean by that is it's removing 98% of the TDS in that water. And that really depends on where you're at in the country with what that means when you're done with it. Places that run off of river water might be at 200 ppm of dissolved solids, or if you're down in, let's say, New Mexico, I've seen well water supplies come up with 1,500 parts per million of TDS. You know, having that 2% remaining of 200 versus 1,500 is a big difference. So talking about reverse osmosis, what does it do? It removes both cationic, so positively charged ions, and negatively charged ions from the water. So pretty much anything from the chlorides, the alkalinities, the sulfates, the list goes on and on. The one thing it doesn't remove is dissolved gases. So if you ever see anything like you need to remove oxygen or carbon dioxide, that's something that this would not be a good place for. So how does it do it? It uses a membrane. The heart of the system is essentially a plastic sheet wrapped around in a spiral that removes it from a couple different characteristics. Try not to go super in depth, but that's really the heart of the system, and what leaves the separation of clean water, which is permeate, and water that's not ideal for many different processes. Reverse osmosis, if you see it in the industry, works on other things besides water. So the dairy industry uses it to separate the different components, the chemical manufacturing, etc. So why do we do this, right? That's the biggest question. Why do we need to clean up this water? Why do we need to spend the money to really invest in this type of solution? And it's really to help mitigate risk around scale and corrosion as we look at, you know, humidifiers that dry steam might also have, different heat exchangers in the industry, process equipment. I'm going to go over some application, what I mean by process equipment, but anywhere from car washes to, you know, agriculture makeup to, you know, if any of you are craft brewery fans, you know, brewing beer, starting with that really good product to begin with and adding in just what you need. So some RO terminology. There's plenty more terminology that can be talked about, but I really thought this is the high level of what do you need to know. So the first thing is what you feed to your RO. Feed water. Inlet can be called pre-treated, filtered effluent, etc. Essentially, the bottom line is what is the one stream going in to the system. The next two lines relate to what's leaving the RO system after it's done its thing, gone through the membrane. The first one is permeate. I've heard it called product water. I've heard it called clean water, as we're really using this on water technologies. And then the concentrate. The names you might hear out there are a reject or a brine or wastewater, dirty water. Really something that is high in TDS, and it collects that on that side of it. Recovery. If you look at, let's say you have one in your house under your sink, you have a little RO system for your house, those tend to work off of city water pressure. Their recovery is typically in the 25% range of recovery, whereas these commercial units can get up to 75% recovery and sometimes even higher depending on the water quality. What the biggest takeaway is, the higher the recovery, the more water you're using as clean water versus going down the drain directly. A slight difference is the rejection. How much of the solids are being rejected from the water? I previously mentioned 98% is the standard membrane that we use to reject TDS. Temperature correction factor. This is a huge point and one where dry steam has a huge strength in the market. we've rated all of our systems at 50 degrees Fahrenheit. For those that haven't worked on these, a lot of the systems are rated at 77 degrees Fahrenheit. And the real challenge there is not too many buildings have 77 degree supply coming to them. I think I've seen it in some Caribbean islands as water source temperature, but it's very abnormal. And there's ways to combat that regarding heating, but a lot of that can be avoided and actually potentially should be avoided because the colder the water, the cleaner the water comes out. The last thing is LSI, PSI, and RSI. As we talk scaling tendencies, we just need to know how far can we push this RO before those membranes scale. And pre-treatment comes a long ways with that softening aspect. So a little bit more about what the heart of the system does as we talk about reverse osmosis. Essentially, there is a barrier, which is the green part in this diagram, which is your membrane sheet. And on one side, you have clean water, and on the other side, you have the dirty water, essentially, coming in. And we're providing a pressure against that. And that pressure is what's really driving through the membrane, the clean water, and leaving the TDS on the other side. Let's see, RO membranes, talking a little bit about maintenance, do require cleaning. The best thing is whether you're out there and you see anti-scalant feeding to prevent scaling, or if you're using a softening technology, that really helps minimize the amount of times the membrane needs to be cleaned. The other aspect to this is if you choose not to clean it, you can replace membranes. I know a couple different places prefer to do that. Essentially, then they don't have to handle the cleaning and the salt, etc. We definitely recommend pre-treatment though regarding softening. Let's see. So we talked about how it does it, but what does it take out? So this depiction in this screen is really showing what does RO do on the bottom left. It can really take out anything larger than this. Just like a sediment filter can take out, sand or carbon or pollen, etc. from a particle filtration perspective. Reverse osmosis gets really fine and really minute particles down to the ionic level, and that's where that aqueous salt piece comes in. Not going to dwell on this a lot, but there are things that we have to be cognizant of regarding ROs, just like the heat exchange surfaces. They can scale, they can foul. We really want to minimize that with pre-treatment and making sure we're operating our system accordingly. So really into why I find reverse osmosis so fascinating is the broad range of applications. And I'm really going to focus in on where dry steam's offering comes in. There's things outside of this like seawater processing for cities. That would be outside of what a dry steam system's designed to do. But focusing on these, car washes. Car washes use this as their rinse water. Everyone wants a nice clean car with no rinse marks or spots from the evaporated water that's leaving the solids behind. Indoor agriculture. They really want to use that RO water as a good foundation and a good base. I mentioned breweries at the same time in this regard because they're using this as their ingredient water. They're giving this to the plants, and those plants absorb the nutrients, which includes what's in the water. So they're taking RO and adding things back in. Laboratory makeup water. They tend to use DI water, and that's one step further than RO. But where the real advantage is using RO upstream of a deionizer to really save capacity on that and to really maximize that investment. High volume printers use RO permeate as well as part of the ink process. Humidifiers, which I assume most in the crowd are familiar with. This really prevents undue maintenance that could be prevented with water treatment and really extending the lifespan of that equipment. The other added benefit is if you have less in the water, you need to drain less frequently, which is true for humidification and steam boilers or other heat exchangers. That's one of the main reasons you're draining it. You've already heated that water up. Why would you want to put it down the drain? Well, it's to protect the equipment. And this is how we can maximize the time between those drains. So talking a little bit about product and reverse osmosis systems, the mineral rejection of our systems, again, is 98%. So if you have 100 ppm coming in, you should expect about 2 ppm of TDS leaving, and obviously that rule can be applied across the board. Extra low energy membranes. One of the things that we found valuable is let's not heat the water, as we could be using this in places that don't necessarily want to heat the water from an energy perspective, or don't want to get that temperature up from a bacteria perspective. So really we can handle this, and we can get a better quality water by using 50-degree water. Something to definitely notice. 100 pounds per hour to 5,500, which equates to about 11 gallons per minute. We use our vapor logic controller, which provides us some nice functionality regarding flush cycles of inequality or of inactivity. And then the stainless steel membrane housings on a slide out rack. If we look at the picture on the right, the RO400 series, one of these advantages is taking out membranes. Membranes last 3 to 5 years approximately with good pre-treatment. And reaching over this equipment while it's wet and the membranes are heavy can be very troublesome, and this is a way to help ease that constraint. So this is a standalone system. The RO200 series has 100, 200, and 300 pounds an hour. There's the equivalent gallon per hour rate. This is definitely an offering that's more on the light commercial or a smaller usage perspective. We design these in Eden Prairie, and we manufacture them in Eden Prairie. Same with manufacturing and designing the 400 series RO. We definitely recommend softened water to extend the membrane life, which we do have pre-treatment both for the softening and dechlorination. Dechlorinated water is required. The thing is, the RO membrane will get about 1,000 ppm hours. So if you have 1 ppm, it can run for 1,000 hours before it's deemed unacceptable from a rejection perspective. But as you're going through time, it's not like it goes from perfect to terrible at that 1,000 hours. It's gradual decrease of quality over time. The other thing is the water efficiency varies by size and membrane staging. As we look at these systems, I think the max is 75% recovery and has different variances depending on the configuration. Again, another chart regarding the temperature aspect of it. If we're looking at others in the marketplace, the typical thing is you might see the RO capacities are rated at 500 ppm of sodium chloride at 77 degrees Fahrenheit. And really where we notice a problem with that is if the customer or the end user is expecting a certain production of water, let's say they need 1 gallon per minute, but are only getting 0.6 gallons per minute, that can be a problem. And really we want to make sure that we're basing our designs off of something that's more consistent with what we're seeing in the industry. So some RO components for those that are new to RO or may not have seen Dry Steam's reverse osmosis offering. This can kind of be universal for most RO systems on the market, except for the controller that's used. Again, I talked about the vapor logic advantage on flush cycles during inactivity, really getting outputs, and the interoperability perspective. Some of the microprocessors on the market give a dry contact relay for a general alarm only. This, you can send the points essentially that you can read on the screen back to a building automation system or building management system. The next thing with pre-filters, most ROs have this. You don't want to remove sand and debris with a membrane. That's a very costly way of doing that. Instead, here the pre-filter is really protecting the membrane system. Directly below that, the high pressure pump. This is what's providing that pressure to overcome the osmotic pressure for the clean water to go through the sheet and onto the permeate side. RO membranes and pressure vessels. Up top is the pressure vessel photo. The membranes go in that vessel and are really the heart of the system. And then on the far right, there's different instrumentation pieces that are in there. You can check out flow rates, pressures, conductivity, all these different things to really understand how your system's performing. Some other options, atmospheric or pressurized. Don't want to go huge in depth. This is more for reference material, but with the atmospheric, we can use a UV system and we provide forwarding. The big takeaway is this comes skid mounted to really help ease installation and make that a smooth transition. This is our overall picture of what a typical system would look like. We don't show the end user downstream, but after that permeate storage tank on the right side of the photo, then it would go to the end user. So some maintenance. What's required for RO maintenance? Really understanding the water quality and how it's running is probably one of the biggest things. In an ideal world, I'm sure if it's a critical process, this is being done daily. Power plants that use RO and then they go one step further to DI water, check their water daily. And a lot of these applications, that would be an extreme. I would not say that there would be a huge benefit for most people to do that from a time perspective. But we really do want to understand versus the other end of that spectrum of never checking is how is your RO performing over time? Is it starting to foul? Is it making its produced amount that it's supposed to, etc. Membrane life, 3 to 5 years again. I've seen as much as 10 years. That would be an extreme, and I've seen as frequent as 6 months, if you don't have good pre-treatment, etc. Pre-filters tend to be, I don't know, probably once a month. What you really need to look at there is when we go back to the pressure gauges, how much has that filter fouled over that time? And then other routine maintenance, check for leaks, replace sensors as needed. Beyond that, you'll kind of come across the majority of that. So some good testing things. There's more information in our IOMs regarding a log of what type of chemistry and what kind of flow rates we're looking at to really help long-term troubleshoot if an issue does occur or if those membranes start to deteriorate or foul. One thing that we talked about was cleaning. What this looks like in our system is actually quite a simple way of doing it. It's as simple as changing out that pre-filter cartridge with one that's either acidic or caustic in nature, depending on if you need to remove scale or organics, or if you need to lay the system up, there's another cartridge that we offer that allows the system to be placed in standby indefinite, for 6 months, let's say in the summer season if you're not using it. Some things to know, well, when do you clean? When your TDS isn't where you need it to be, and it previously was. If a differential pressure across the membrane increases 15% from new, or that permeate flow decreased by 15% over that time. So my last slide before we get to questions, what do you guys need to know in the field to really understand how do we size and how do we apply this technology? The first thing is, what type of application is this? Is this going to feed a heat exchanger? Is this going to feed a laboratory? Is this going to feed a printer, etc.? What's the total usage per day? And as we look at that, a lot of the ROs, including our own, have how many gallons per day it can produce, as well as what's its flow rate per day. We want to make sure we size accordingly so that you can have some maintenance time and you have some safety factor along with what that total usage is. What the usage flow rates are. This is really critical for when we talk about the storage tank. If you only use 1,000 gallons per day, for example, on your total RO usage, but you're using that in a 30-minute span, well, if the RO is either A, not big enough, or the storage tank isn't big enough, then we really need to make sure we understand what that requirement is and choose it appropriately. What's the water quality coming in, including temperature? We want to make sure that this isn't seawater, for example, or this isn't brine water, intruded well water. What's the outlet? What's the goal? What do we need to get to make sure that that piece of equipment or that customer is happy? Available space, there's definitely clearance requirements for all of the pre-treatment and for the ROs. What are the electrical requirements? And then, are there any special requirements? Is there a customer asking for high rejection, like a 99% rejection? That would be something good to know, that, you know, our standard's 98% and they're saying they need 99. Well, we need to work through that. So with that, I'm going to open it up to questions, and it looks like we have a couple in. So the first question is, how would the product compare to a Culligan system? Are we targeting the same market application competitiveness? So to answer that, it's quite comparable from the basic items. You know, it's got a frame, it's got a pump, a controller, membranes. We didn't do quite a competitive deep dive, but some of the really differentiators that our product line has in comparison to the Culligan offering is extended warranty, for 2-year warranty on that product, with the ability to purchase more. The Vapor Logic controller and its capabilities regarding the inactivity flushes, the communication protocol, and then looking at the maintenance aspect of that system. The other things that, from a comparative perspective, that are similar but slightly different, you know, some Culligan systems might have fiberglass membranes versus membrane housings versus stainless steel. That's really a preference-driven thing. So let's see, next question here. If the water is warmer than the 50-degree Fahrenheit rating, how does that derate the unit's capacity? So if it's warmer than the 50 degrees, it will increase the flow capacity of that system. And it's a trade-off. I mentioned a little bit about the colder the temperature, the better the output from a quality perspective, but we're going to slightly gain capacity as that temperature goes out. The best piece of reference for that is referring back to that chart that I presented regarding that multiplier, essentially relating to the flow rate of the system. Can these be placed in series to increase their ability to remove TDS? That's definitely a great question. What that refers to is, can these be 2-pass systems? A 2-pass RO is taking that second system and using permeate from the first. To do that, if that's something that's required, we definitely want to have a conversation on it. It can be done. It's quite frequent in the industry. It's just something that needs more discussion as you come across those opportunities. If application is winter humidification, what has to be done for summer shutdown and fall startup? So as we go back to maintenance, so we talked a little bit about how the RO will flush with inactivity. over a certain period of time, that's really not a good month-long solution. If you plan on being laid up for more than a week, really the best thing to do is use a preservative cartridge in that system. And in our IOM that we talk about the process to doing that, but essentially it's taking that cleaning cartridge, putting it in the system, letting the system flow until you get that solution into the membranes, and then turning off the system from power perspective. If we don't do that and we leave, if someone flips the circuit breaker on that leg of the system, since we're not going to be using it for the year, the real risk to that is biological growth as we talk about stagnant water. Now, after that preservation solution has been there, when you want to do fall startup, that essentially entails turning the system back on and flushing that system to drain and not down to the downstream user to then bring that water quality back to what it was during operation. Next question is, in addition to flow rate, do we also need to be aware of pressure needed to deliver the RO water to point of use? So that's a great question. With that question, it's something as we talk about plumbing and as we talk about systems, we really need to be cognizant of on the design end. We didn't talk about that today, but the high level overview is if we have X pressure in this bladder tank, or if our pump can pump X amount of pressure out, if we have an RO down in a mechanical room in a high-rise building, for example, and we need to go up 10 stories, well, what's really driving that pressure up? We need to be cognizant of that when we're sizing these applications. Kind of going back to those space constraints, and where are we placing the equipment? Where does the water need to get to, and how do we get it there is the best thing to think about. Good question. As you have a water storage tank, do you have any method in order to avoid bacterial Legionella growth? I read something about a UV lamp in the presentation. So the one thing is with Legionella specifically, that's a good point of where we want to keep that temperature lower than higher. According to ASHRAE and other health sources, Legionella specifically proliferates in a warm zone. So I believe the latest was 68 Fahrenheit to 113 Fahrenheit. So if we can really keep it below that, that's going to help us, along with keeping stagnant water out of the system. That's good control in general. So talked about flush sequences, the UV portion. So atmospheric storage tanks, unlike pressurized storage tanks, have that aspect of they're open to the air. Within our offering, to help mitigate some of that risk, is a recirculation method with that pump, which then would go through a UV system to then kill bacteria. Obviously, it can only kill the bacteria that the UV light sees. But this is another thing where we need to make sure that maintenance is being kept up to date, we're keeping water moving, and really understanding the risk associated with the different applications. See, next question. What is the average unit lifetime before replacement is necessary? I'm going to assume that is the RO system as a whole. So regarding the system and the guts of it, 10, 15 years, very similar, on plus, depending on how well it's maintained. The consumable pieces of that equipment would need to be replaced more frequently. So that could include things like pressure gauges, for example, or the pre-filter cartridge, the RO membranes. I mentioned 3 to 5 years is a typical lifetime. And any seals and gaskets that might swell or deteriorate over time. Let's see, next question is it preferable to install dechlorinator filter before the softener or before the RO system? Another great question, and actually that is a point of contention in the marketplace and in the industry. It really depends on what your goals are. So if you have soft water existing in the building and you're feeding our system with soft water, then the dechlorinator would go in between the softener and the RO. When we use our sizing software, we tend to put the dechlorinator in front of the softener, and then the RO goes after the softener. There's pluses and minuses to both, and really depends on what your goals are, and either way we're flexible in which way it goes. I guess I should mention everything that's written in the IOM is from the basis of dechlorinator first, softener, then RO. Is RO complementary to UV treatment? So the RO has kind of a different function regarding its end purpose goals. I know that one slide regarding the filtration spectrum mentioned bacteria and viruses from a microscopic level as being removed by RO, but I would consider the UV to actually be more complementary towards the RO, the UV to the RO. As each has a different function, RO isn't directly sanctioned to remove bacteria, and that being the only treatment method. And even beyond that, depending on application, UV might not be the only type of disinfection used either. Please note the peak temperature of the membrane can see hard to find in your literature. So regarding the membrane maximum temperature, we really want to operate the system between 50 and 77 degrees Fahrenheit. The membrane itself can technically go up to 113 degrees Fahrenheit. That would be a document that's provided under our vendor cut sheets as we're looking at submittals. And that's dictated by the membrane itself. Other componentry in our system, the things that we definitely don't want to see 113 degrees, even though it can, as PVC, inlet piping, etc. So if you have a higher temperature from a peak perspective, please get in contact with us and we can work through that. What piping materials should be used downstream of an RO? So the best types that are most typically used in the marketplace would include any plastic type materials, so PVC, CPVC, stainless steel, whether that's 304 or 316, and some more obscure things. If we're talking a smaller RO 200 series, like a polyethylene or polypropylene tubing, as we're talking the 3/8 inch size OD, would be very typical for that application. Let's see here. Sorry, I'm scrolling here. My computer's acting up. Loop piping should have minimal dead legs and return back to storage tank. Yeah, definitely a good comment. So the loop piping within our own skid is probably, I don't know, 7 feet worth of piping as it goes from the pump discharge up through the UV system and then back horizontally to the storage tank. What is the maximum TDS for the inlet water? If we are over that number, what can we do to solve that? So as we talk about the ratings of the system and its capacity, so one of the pieces that we talked about was the temperature aspect of TDS and how our system's rated. If you have more TDS in the water, then you need more pressure to overcome to then push the clean water through the membrane. The maximum, I believe, is, and I can definitely get back to you, I think we have 1,000 ppm of TDS. I can definitely confirm that for you. What about the hygienic problems when using a dechlorinator and then accumulate permeate water in a pressurized storage tank? So that's definitely something to be cognizant when we're designing. We don't want to oversize the system and cause stagnant water because we don't have that demand going on. And then again, mitigating that risk and essentially understanding that application. So for example, there's other applications out there like water for injection, for human injection. This type of system would not be appropriate for that from a hygienic perspective, as we look at that kind of medical level of water. But that's where we really just need to understand what's the goal, what do we need from a water capacity, and what risks are associated as we talk through those applications. And I think that's it for questions. And Abby, do you see any other questions out there?
I do not. Nope. All right, everybody. Thank you for attending our webinar on reverse osmosis systems, and have a great rest of your day.